Hello, my name is Oleksii Vodka. Today I am going to speak to about acceleration 3D microstructure generation using parallel Cellular Automata algorithm. I am from National Technical University Kharkiv Polytechnic Institute, from Department of Mathematical Modeling and Intelligent Computing in Engineering, which is part of Institute of Computer Modeling. Today, we develop an software and which calls MatViz3D, and we would like to introduce our results of research how to speed up microstructure generation in this software. First of all, microstructure is one of main characteristics of polycrystal material, which used to build models of deformation of polycrystal materials, and this structure significantly influence of mechanical and thermal properties of such materials. To effectively generate such microstructures, we use a Cellular Automata method, and its method can be parallelized using different techniques. About one of techniques we speak today. And we focus only on CPU parallelization due to universality of such approach, because there are not any popular libraries which can parallelize algorithm for different GPUs, and only CPUs for today can be used effectively from different manufacturers and different models with the same code and the same type version of library. So to do this, we use special library which calls OpenMP to perform automatic parallelization and perform some additional manual tricks to parallelize our code. So what we do to measure to measure effectiveness of parallelization, we develop some parallel algorithm for microstructure generation and measure two factors which call speed up and efficiency. The formulas of which you can see on the slide. Speed up shows the increasing of shows the decreasing of time of execution compared to the one time of one thread, and the efficiency shows the divergence from linear increasing of performance of speed up with increasing number of cores. So we develop our own algorithms which allows us to perform such modeling using parallel algorithms, and the main difference from any other classic approaches is the next. All other researchers perform algorithms, they divided the area of Cellular Automata by the parts which processed by own threads. In our approach, we suggest the cells which can grow in the next iteration. So we collect this possibly growing gray cells in the array and parallelize the processing of such arrays. So we reduce the complexity of such algorithm from cubic to linear with some special tricks. So let's look close on this algorithm. We start as usual for creating grids for voxels from array n by n by n, generate initial points of crystallization, and we write this point for array of grains that could be growth in the next iteration. After that, we divide these arrays into several processors, several cores, and perform the next part that you can see in the middle column of our algorithm. We create local grains array and divide this big grains for local grains, and for I is equal to 0 and until the all grains is processed, we check the neighbors of all grains and the boundary condition that if all conditions met, we consider that voxel can grows and grows and next generate next grows the next voxels and next cells, and we update voxels array and record this new voxels to the grain array and increase the number of I and perform this until all grains not processed. After that, we combine all results that get from the grain algorithms and combine it together, clear global grain arrays, and obtain new grain and voxels, and start this algorithm from very beginning and proceed this grain arrays, etc., until all voxels uh, would not filled and we got entire microstructure. Let's see on visualization. Let's look on visualization for different algorithm. You can see the for Neyman, Moore, radial, and probability algorithm visualization that generated using MatViz3D. To perform tests, we use different types and different generation of processor. We use Intel processor, also like a AMD processor. That's all we can find from our neighbors, teammates, etc., and send them to providing this processor for testing. You can see the release, the year of release of such processors depend from 2017 up to 2023. And one main point, new processors contains not only virtual cores, the new things that contains energy efficient cores. As you can see for the first and second processors, they contain 4 and 6 productive cores and 4 and 9 energy effective cores. And this may lead significantly to the performance our algorithm of using these algorithms. So let's look on the result. First of all, we're testing this algorithm using speedup matrix. The red line shows the theoretical speedup. When you, for example, would like to use 10 cores, you should give 10 times the speedup. But real life shows the lowest values. This test performs for cube size of stupid. This test performs on cube size 150 voxels, and the initial concentration of voxels is equal to 5%. In this graph, the dashed line showed for orange and the blue line and the green line showed the energy effective cores that enabled after all main cores is used. So you can see the energy efficient cores has significantly low performance and reduce the total speedup of these cores, but still increase the total speedup for this algorithm. You can see the same uh, thing for Neyman, for radial algorithm. Also, we perform for Moore and probability algorithm, and the main results approximately the same. After that, we increase the size of cube up to 350 and concentration also keep the same 5% and perform this test again, and you can see for biggest size of cube you can get a little bit bigger performance as speedup coefficient for energy effective cores, and the same you can see for processor, for example for violet line where the speedup nearest to theoretical one. This is a classical processor without any energy efficient cores. The same for Moore algorithm and the probability algorithm. Also, we calculate the efficiency, and you can see the efficiency significantly reduced by increasing the number of cores, but the lowest reduction shows the oldest processor i5 8400, and the biggest speed up shows a the biggest drop of the efficiency shows a modern processor with good energy efficient cores. The same you got for Neyman for radial algorithms. You can see it's too close for i5 and i9 processors. The same for Moore algorithms and the probability algorithms. And if we increase the size of our cube, so increase the amount of calculation, we got the same result for biggest efficiency demonstrate old processors and the lowest efficiency demonstrate new modern processor of 12 and 13 uh, generation of Intel processors due to implementation energy efficient cores. The same for Moore and probability algorithms. We collect all this data for in the table, and you can see the worst value demonstrate i5 14500, and the highest performance demonstrate i5 8400. You can see the 8400 demonstrate near 85 95% efficiency, and others demonstrate only 75% of efficiency. So that shows the influence of this energy efficient cores. And as a conclusion of this part, you can see that the energy efficient cores definitely influence of all computational efficiency and makes a big impact, but it allows to increase the productivity with increased numbers of cores without increasing the amount of power supply, which was good for mobile platforms. So, as a global conclusion for this research, um, in this work, we developed the parallel algorithm for 3D master generation using MatViz3D. The performance has been analyzed using different algorithms and different hardware with more algorithms and other algorithms, and the more shows biggest effectiveness with respect to others. We test the scalability and understand the scalability can be improved for high numbers of cores, and we should be distinct the effective cores, energy effective cores, and classical cores, and we need to understand how it works with them to get bigger performance. Also, we see that limitation on TDP for mobile process also lead to decreasing of performance, and the desktop PC shows a high performance to compare with mobile due to limitation of TDP, and classical desktop computers got a better cooling system. It also got bigger TDP and bigger performance. In the future, we are going to optimize our algorithms to perform load balancing and reduce synchronization overheads, and going to improve this algorithm for further steps. Thank you for attention. If you had questions, please write me an email. See you.